Okay, welcome to topic 14, topic of heat. So this will be a little bit longer than temperature, but we'll fly through pretty quick. This topic, generally, people have difficulty in creating the equation, but once you've it done, you fly through it. This topic is easy, guys. You should be looking, if this question comes up, you should be looking to pick up all the points. And there's basically 2-3 equations that you use, and you just use them over and over. However, where this question can often come up is part of an electricity question, i.e. how much electricity would we use if we were to turn on the kettle and boil half a litre of water. Okay, so that's kind of the idea here, is where this kind of puts in. So I'm going to go through this pretty quick. You see now on the notes, there are 10 notes. In total, there is 7 questions. So there's only 7 questions, 10 pages, so we'll get through it pretty quick. I'm going to skip through a lot because obviously a lot of it's self-explanatory, like obviously solid, liquid, gases. Heat is a form of energy, you should know that. What we're going to deal with first here is heat capacity, okay? What does heat capacity mean? It means the amount of heat energy that you would need to put into the object to change its temperature by 1 degree Celsius, okay? So generally what happens is that everything has a heat capacity. The amount of heat is a form of energy, okay? The reason things feel hot is that the molecule or the particles in it are vibrating, okay, and they're moving, and that's why it feels hot, okay? So generally, the heat capacity means if you want to heat something up by 1 degree Celsius, how much energy do you need to pump in to get that up, okay? So, for example, water, how much would you have to get into water to heat that up? Metal, how much would you have to pump into metal? The air, how much would you have to pump into the air, etc., okay? The SI unit for heat capacity is joules per Kelvin, and it's a capital C. Okay, now there's a reason for that. We'll be coming back to something else. Obviously, excuse me. I haven't had my morning coffee. So the wiser of you will notice that there's a flaw with this, i.e. how much energy do we need to raise temperature of water by 1 degree? How much energy do we need to raise temperature of metal? So see, can you figure out what factor are we ignoring there that we need to pop in later? So generally the equation, which is in your log tables, is Q equals C delta theta. Okay, Q equals C delta theta, Q being for energy, okay? Oops, hit the wrong thing there. All right, okay. Now, specific heat capacity is what you're going to use nearly all the time. So, did you realize what we were missing? What's the difference? Specific is small c, heat energy needed to change the temperature of 1 kg by 1 Kelvin. You see, that's the difference. Heat capacity, if you noticed, there was no discrepancy. It just said, how much do I need to heat up water? How much do I need to heat up? And then obviously, you should realize that there's too many variables. It's the big thing about science is you have to count for all the variables. So here we're going to say, okay, well, specific, hence why it's specific. How much heat do we need to change 1 kg of object by 1 Kelvin or substance? Hence why its SI unit is joules per kg to the minus 1 per Kelvin to the minus 1. You see? And if you said 1 kg by 1 degree Celsius, generally they accept it as well. Okay, now, as you can see here, the energy needed to produce a given raise in temperature is proportional to the mass of the body, okay? Big one though, provided it does not change state, okay? So for this, we're not looking at, if you pump the heat energy in, and all of a sudden it changes into something else, well, that's wrong, okay? We need to find out how much energy, when you turn on the kettle and the water is, we'll say, 10 degrees, and you want to bring it up to 100 degrees, well, how much energy do we need to get that amount of water, 10 millimeters from 10 degrees up to 100 degrees, okay? So, you're left with Q equals MC delta theta. Specific heat capacity, rise in temperature, fall in temperature. Note, whether it goes up or down, it always has to be positive, okay? Because it's the change. How much did it change? In other words, we went from 100 all the way down to minus 10, okay? Or actually, it's way too large. It'll never be something like that. I would say 50. So therefore, what's our change in temperature? What do we change? 60. Change is not minus 60, 60, okay? So the change in temperature is always a positive number, okay? It has to be a positive number. So if it's a rise in temperature, I usually do final minus initial, If it's a fall, initial minus final, and you'll get your answer there, okay? General rule of thumb has to be a positive number there, okay? All right, so the first thing here then, problem 1. A calorimeter of oil has a heat capacity of, now I will write we're going to have to do this. So these questions, these maths questions can get very large. So I will write my stuff out on the left-hand side, but I'm going to have to rub it out, okay? Because I'll need space. I'm going to write up on the left-hand side, rub it out, and then write the equation, okay? But you obviously can write it into your notes and keep it there. Calorimeter of oil has a heat capacity. So heat capacity of oil, 1500 joules per Kelvin. And how much energy is needed to raise its temperature? So the change in temperature, so it's rising, so it's final minus initial. Okay, how much heat energy is needed? There we go, that's it. So we're not using specific heat capacity here. We're going to use heat capacity because it didn't give us a mass. So if they don't give you a mass, you can still answer it. So we're looking for Q equals C delta theta. So Q, that should work out to be 105,000 joules. Okay. Okay. The next question then, you can't get questions like that. I mean, it came up in an exam paper before. The first question was how much energy would you need to heat the spoon made up of tin up? And then the next question was how much would you need to heat up so much water? So you can't come up this way. If you don't get the mass, you use that equation. Okay, problem 2 now. Some strange noises coming out of the other room. Okay, so problem 2. If 40,000 joules of heat energy is applied separately to both 2 kgs of copper at 0 and 2 kgs of aluminum at 20, which reaches the higher temperature? And we were given the 2 heat capacities there. Okay, so first things first, you can squeeze this one in. Write everything you have on the left-hand side. So the amount of energy we have is 40,000 joules. 2 kgs of copper, so the mass of copper is 2 kgs, and the mass of aluminum was 2 kgs, and the initial temperature of copper was 0, and the initial temperature of aluminum was 0 or 20, sorry. And we have the heat capacities. I'm not going to write out the heat capacities because they're just there. Heat capacity of aluminum, heat capacity of copper. Oh, right, okay, we'll write them out. You really should write them out. I'd always advise write them out. I'm just trying to be lazy here. 910 and heat capacity of copper 390. Okay. So the question is, what is the final temperature? Because we want to find the higher temperature. So what we're going to look for is we're going to look for final temperature of copper and final temperature of aluminum. And then we're going to find out which one reaches the higher temperature. Okay, so I'm going to start first with, it doesn't really matter what you start with. You can start with aluminum, but I'm going to start with copper. Right, so the equation we're going to use is Q equals mc delta theta. So we're rising the temperature. So there's 2 ways we could do this. If we want, we could break delta theta into final minus initial, okay? And then multiply the m and the c into both and divide it across, but that's going to be very difficult. So instead what we'll do is we'll keep this separate, and we'll just say delta theta equals q over mc. This might be a little bit easier. We'll put in our values for copper, because we're doing copper first. And we should end up, so that'll be 40,000 over 2 times 390. So we should end up with our temperature change being 51.3 degrees Celsius. Next we'll do aluminum. Same thing again. Q equals mc delta theta. Change in temperature is q over mc. So our Q, again, is 40,000, but our mass is 2, and our heat capacity is 910. So we end up with 22 degrees Celsius. Okay? So the change in temperature for copper was 51 degrees. And the change in temperature for aluminum was 22. So that's not the final, that's the change in. Okay? So change in temperature, because it goes up, is final minus initial. You see? So therefore, final temperature is going to be change in temperature plus initial temperature. You see? So for copper, 0. So therefore, the final temperature is 51.3 degrees Celsius. And the final temperature for here, because here the final temperature is going to be 22 plus 20, which is 42 degrees Celsius. So therefore, copper reaches a higher temperature. You see? A bit easier. The other way, guys, was you could break the change of temperature into your final and your initial. And then multiply MC into both, and then bring everything to the one side and leave the unknown and divide across, and you get the final temperature as well. So you could do it that way. You could. You still get the same answer. But I find this way is just a little bit easier, okay? A little less confusing, okay? All right. Problem 3. Now this one I will have to, I'm going to write out the values on the left-hand side so you can see them. But then I'm going to have to rub them out because I'm going to need all the space. This is more common of what your questions are going to be like. Now they will add in latent heat, which we'll cover in a second. Latent heat is an important one as well. So what I'll do is I'll write everything on the left hand side just so you can see the conversions, etc. And then I'm going to rub everything out and I'm going to show you how to write these equations. There's lots of maths involved in this, and what I advise with these questions, take your time, don't skip the step, do everything one after the other, okay? Because if you skip a step, you probably make a mistake. All right, so we'll read it through it first. 120 grams of copper at 100 degrees Celsius are added to 80 grams of water in a 60 gram copper calorimeter at 20 degrees Celsius. If there is no heat loss to the surroundings, find the final temperature of the system. Heat capacity of water is 4180, and the heat capacity of copper is the same as up here, 390, okay? Okay, so write out everything you have, all right? So, all right, okay, sorry, the tablet seems to be working. Mass of copper, 120 grams. So we have to convert that to kgs. 0.12 kgs. I do apologize, guys, for the handwriting, but when I'm writing on this tablet, I mentioned it before, I have to basically try and write in a very awkward way, because if anything touches the screen while you're writing, it won't record the screen right. So my handwriting's bad enough as it is, and this makes it worse. So mass of water, 80 grams, 0.08 kgs, and copper, calorimeter, so mass of calorimeter, 60 grams, 0.06 kgs. Okay, so then we look at initial temperature of copper, 100 degrees Celsius. Initial temperature of water, 20 degrees Celsius. And initial temperature of calorimeter. How are they 20 degrees Celsius? The water and the copper, you assume, are the same temperature. So if the water is in the calorimeter and the temperature is 20, then that means the water and the calorimeter are 20. Because if the water is hotter than the copper calorimeter will take the heat energy and cool down the water so they're at the same temperature, and vice versa. If the copper calorimeter was warm, we pour the water in, the water would take the heat from the calorimeter. So generally it's the same, okay? So we're trying to find the final temperature of the whole thing. So that's what we're trying to find, okay? And heat capacity of water is 4180, and heat capacity of copper, what did we say in the previous question? 390, okay? So they're all our values. So you write them all out on the left-hand side. Now you need to write them all out on the left-hand side, because what we're going to do is I'm going to have to rub them out, but we're going to have a large equation. So this time, writing them out on the left-hand side is vital, And as you fill them in to the equation, you tick them off. Okay, so each time you put something in, you tick it off to make sure you have everything included. Okay, all right, so there are all your values. Now I'm gonna have to rub this out, but you can always go and bring the video back to look at them. Okay, so we will start then. Oops. If you think you know what to do, you can make a start and move ahead. It's perfectly fine. Okay. So I'm going to roll it down so I can make as much use of space as possible. All right. So what I generally do, we start with, in these kind of systems, if I pour something hot into something cold, what's going to happen? The something hot is going to cool down. If I pour something hot into something cold, what else is going to happen? Something cold heats up. So something's going to lose heat. Something's going to gain heat. So that's where we'll start. So we start with heat lost by. So I always put the heat loss on the left and the heat gain on the right. So what's losing heat here? Copper. Anything else? No. Copper's losing heat. So heat gain by. Who's gaining heat? Well, the water. Anything else? Something else has to gain heat. The calorimeter. So heat lost by the copper, heat gained by the water, and heat gained by the calorimeter. So there are going to be 3 different things going on here. So that's the first step. And I always put that in red, just kind of highlight it to it. So let's start with the copper. What do we have? Mass of the copper, specific heat capacity of the copper, change in temperature. Now, tell me, heat lost, is the temperature going up or down? Down. So it's losing heat. Mass of the water, heat capacity of water. What's happening to the water? Temperature, it's going up. Plus mass of the calorimeter, heat capacity of the calorimeter. And of course, if the water and the temperature is going up, its temperature is going up. So there we have it. Our equation is now set. You see? So now after this, we just fill in our values. The only thing we'll have to be careful of is here. What do we put in here? Now I'm going to show you what I told you before, that if you're gaining heat, you do one thing, and if you're losing heat, you do the other. But there's another method too, that if you forget that, that you can do, that will work as well. It'll end up working out in the end. Okay? So don't worry too much about it. All right, so this is where it can get a bit messy. So we got to squeeze in all our values across the board. And this is where people find it confusing because there's mass numbers now going to come in everywhere. So mass of the copper is 0.12. Heat capacity is 390. Because we're losing heat, what did I say? If you're losing heat, it's your initial minus your final. Mass of the water was, where did I have the water here? 0.08. Heat capacity of water is 1480. And what do we say for gaining heat? Final minus initial. Mass of the calorimeter, 390. Now, you see? So that's why I was telling you, if you're losing heat, initial minus final. If you're gaining heat, final minus initial. Now, if you find some people have, like personally, can't learn things off, I have to understand it. So if you kind of find that you can't learn it off and you're getting it wrong all the time, notice something else. On the left-hand side, okay, it is your number minus the unknown, and on the right-hand side, it's the unknown minus the number, unknown minus the number. In other words, if you have final minus initial on the left-hand side, make the right-hand side initial minus final. If you have initial minus final on the left-hand side, make the other side final minus initial. Whatever you do on the left-hand side for the temperature, do the opposite on the right, and it should still work out, okay? So if you got it wrong, let's say you had here theta minus 100. Well, if you keep this theta as minus 100, you're going to go wrong. But if you made this 20 minus theta, 20 minus theta, you'd end up with a minus number here, a minus number, and minus numbers here. But it would work out because you'd end up, when you bring everything to the other sides, the minus numbers would cancel and you'd end up with the correct answer anyway. Okay, so don't worry too much about that. You should do it this way, but if you find you can't learn it off, can't remember, simply do it this way. Whatever you do to the left hand side, if you have final minus initial, make the other side initial minus final. Okay? All right. Now we will move on. So this left hand side should end up working out to be 4,680 minus 46.8 theta equals 334.4 theta minus 6688 plus 23.4 theta minus 468. So we bring all the thetas to one side and we bring all the numbers to the other, and that should work out to be 404.6. I'm skipping steps obviously, guys, because I'm cutting a bit of time. 11836. So theta should work out to be 29.25 degrees Celsius. Done. You see? That's how you do it. These questions are fairly straightforward. Where people go wrong is trying to do the maths. You just simply multiply everything in. You multiply these two brackets first on each side. Then you multiply that into the two values here, and that's why I end up with this. Bring all the unknowns to one side, all the numbers to the other. It's algebra, guys. Basic algebra. Okay, we will move on. Storage heaters they haven't really come up much anymore, but generally how they work is, know them in case it could get asked, all right, is they're basically bricks with a high specific heat capacity, okay? So what happens is that at night the electricity is on and it heats up, so they take in a huge amount of heat, so they take in a lot of heat energy to change the temperature by 1 degree Celsius, okay? So you turn on the heat, the electricity is pumping through it. Now a lot of people say these are more efficient because what you do is you turn them on at night and they get hot and hot and hot, but you keep the vents closed so the heat is inside the machine, it doesn't come out. So this thing heats up. So then what you do is when you open the vents, you turn off the electricity. But because they have such a high heat capacity, they took in a huge amount of energy to get their temperature up. Then during the day, the electricity is turned off, but they have to give out that heat energy to go back down. So they release a huge amount of heat energy. So they work out to be pretty efficient. But generally, they only work in factories and things like that. Usually people who have them in their homes, if they have them, what they do is they turn them on for like maybe 2 hours and then turn it off, and it will pump out heat for the next 6 hours. You know, they're very efficient like that. Okay, latent heat. Hopefully you remember this from junior cert. If you did it in junior cert, you should have. So generally what you have is when things melt, the temperature tends to go up. Then all of a sudden it levels off. Then the temperature spikes again, levels off, spikes again. Okay, so the temperature rises. Now you were just told latent heat, hidden heat. Most people probably didn't explain to you what's going on there. What's happening is that the heat is still going in, the energy is still going in, but it's being used up differently. So instead of being used to raise the temperature, it's being used to change the state. So the object is no longer just getting hotter. It's changing from one thing to another, solid to a liquid, liquid to a gas, or vice versa. Now for us, there are two different types, fusion and vaporization, and we'll get to them in a second, and you need to know the difference between the two. So latent heat, if you are asked, latent heat of a substance, heat energy needed to change its state without a change temperature. Please state this bit at the end, without a change temperature. Okay? Because if you forget to state that, you're wrong. Okay? Now, if we're going from a solid to a liquid, or a liquid to a solid, that is fusion. If we're going from a liquid to a gas, gas to a liquid, that is vaporization. How can you remember that? Simple. Look at the word vaporization. Vaporization sounds like something's turned into vapor, gas. You see? Think of it that way. Vapor, gas. So fusion is solid. So solid to a liquid, liquid to a solid, fusion. Liquid to a gas, gas to a liquid, vapor, vaporization. Okay? SI unit, of course, is the joule. Okay? And latent heat is an L. So here you are. These are your three that you need to know. Specific. Again, very similar to the previous one, except we're including the fact that there's a mass here. The amount of heat energy needed to change the state of 1 kg without a change of temperature. For fusion, need to change 1 kg of a state from a solid to a liquid without change of temperature. Vaporization, 1 kg from a liquid to a gas. And there you go. Joules per Kelvin is the SI unit. And the equation you see in your log tables is this one. Q equals ml. Okay, now let me see. We have 1, 2. Okay, so I have 3 questions to do with you. And then we're kind of done, really. There's a few kind of little bit teasing. I'll do 1 or 2 of them. I'll skip most of them because they're junior sort of stuff. It's just kind of, it's there, it's on the course, but you should know it anyway. All right, so these questions, the first 2, fairly straightforward. The third one is long. And the third one will be now very, again, typical of an exam paper question. But once you do it, you realize they're all the same. That's the thing about heat. They're all the same. It's the same thing over and over again. Okay, so for question 1, I'm not going to write out all the values because it'll just take too long. So, and they're there in front of us anyway. How much heat energy is needed to completely convert 10 kgs of ice at 0 degrees Celsius to water at 0 degrees Celsius? Okay, so Q equals mass of ice times, there's no change in temperature, so we're going to have to do latent heat of fusion. Okay, so if the ice is 10 degrees Celsius, latent heat of fusion is 3.3 by 10 to the 5 kgs. So therefore that should give us 3.3 10 to the 6 joules. Okay, why is it joules, why not joules per Kelvin? Because mass is kg, latent heat of fusion is joules per kg, which basically means kg joules over kg. Kg cancels kg left with joules. Okay, that's where it kind of comes from. All right. How much heat energy is needed to convert 1 kg of ice at 0 degrees to steam? There we go. Now, this is a little bit different. Okay, I don't know why that's... So, Q equals... So what's the first thing that's going to happen? So this is how we're going to have to phrase this. What's the first thing that's going to happen? Ice at 0, when we start adding heat to it, it's going to melt. So mass of ice, latent heat of fusion. So what's going to happen then after the ice melts? We're left with water. What has to happen to the water? Has to heat up. Add mass of ice, heat capacity of water, change the temperature, temperature is going up. And then what happens to that when we want to get it to steam? It's going to change. Mass of ice, latent heat of vaporization. You see? Now, the mass of the ice is 1. Latent heat of fusion, again, I'm going to try and just speak it out to you guys, is here. Fusion, 3.3 by 10 to the 5. Heat capacity of water, 4180. And latent heat of vaporization is 2.3 by 10 to the 6. Okay? So your Q value, when you put all those values in, just calculator work, should be 3.05 by 10 to the 6 joules. There you go. Okay, so the last question now. So like the previous question with latent heat, or with heat, I will write the values out. Okay, so I'll write them on the left hand side so you can see them and convert them to make sure you are correct there. And they're going to have to rub them out because I'm going to need the whole page in space, and I'll go through it bit by bit by bit. So we'll read the question first and then we'll do that. So 2 grams of steam at 100 degrees Celsius are added to an insulated calorimeter containing 8. This is very similar to your experiment actually. It's an insulated calorimeter containing 80 grams of water at 10 degrees Celsius. Find the resulting temperature of the mixture, assuming the calorimeter has negligible heat capacity. In other words, no heat is given out. The calorimeter is made from copper and has a mass of 70. So in other words, for the first one, we're going to assume that the calorimeter plays no part. That's the idea. And in the second one, it does. Okay, and of course it would, but you know, that's what they're doing. So we'll write out everything first. So mass of the steam is 2 grams. So that's going to be 0.002 kg. Mass of the water is 80 grams, 0.08 kgs. Initial temperature of the steam is 100 degrees Celsius. Initial temperature of the water, 10 degrees Celsius. And the heat capacities, so now we need extra values, sorry. Latent heat of vaporization, 2.3 by 10 to the 6. heat capacity of water, 41880. 4180, I think that's everything. Yeah. Okay, so we have all our values there. Okay, so I'm going to rub them out now so you see that you have them. Make sure that you're correct with your books or your copies. Right. So again, like the previous one, we start the same way. We're adding something hot to something cold. Okay, so we start with heat gain by. Heat gain by what? Oh, apologies, not heat gain. It should be heat lost on the left hand side. Heat lost by, what's losing heat? It's going to be the steam, isn't it? So if it's losing its heat, what's gaining it? The water. Okay? So, now we start on the left hand side and we look at our equation. So we have steam at 100 degrees Celsius and we're going to put it into water. What's the first thing that's going to happen to that steam? It's going to have to change state. So mass of the steam, latent heat of vaporization. We now have water. Once it changes state, there's no change in temperature, so that water is 100 degrees Celsius. So what's going to have to happen? It's going to cool down. Mass of the water, heat capacity of water, change in temperature, down. All right, the water, what's going to happen to the water? Is it going to change state? No. Okay, it's not. We know that because we're adding 2 grams of steam, so it's not going to be enough to change the water. So we know the mass of the water, heat capacity of water, increase in temperature. Okay, put in our values. So the mass of the steam is 0.002. Be careful there, I did this earlier. My notes, I made a mistake. I forgot it was 0.002 and I put in 0.02. Okay, so be very careful. That's why I say write everything out on the left hand side and keep checking back to your numbers to make sure you put it in correctly. Okay, this is the kind of place where mistakes will be made. You put 0.02 instead of 0.002. Okay, so just be aware. That's why I always say right out on the left hand side, double check. 2.3 by 10 to the 6 plus 0.002 4180. Now we're going down, so initial minus final. Now I'm going to put the right hand side, because I'm out of space, below it. So equals 0.08 4180 final minus initial. Okay, and again, look at this. I know the initial minus final is, but if you forgot, I had here initial minus final, so on the other side, final minus initial. Okay, so I flipped it around. Okay. Now, do the maths. On the left hand side, we should, just checking to make sure I did my numbers correct here. Yep. So on the left hand side now, 4600 plus 836 minus 8.36 theta equals 334.4 theta minus 3344. Bring all the thetas to one hand side and all the numbers to the other. 342.76 theta equals 8780. Trying to read my own handwriting. So theta should equals 25.616 degrees Celsius. There you go. Okay. So again, I know I skipped steps, but that's because I wouldn't be able to fit it all in. Okay. So basically, multiply everything out. Okay. And then bring all your unknowns, the thetas, to one side. And when you're doing the equation, if you do initial minus final on one side, make the other side final minus initial. Okay. You should know the difference anyway. If you're going down, it's initial minus final. If you're going up, it's final minus initial. Okay. So I'm going to rub this out because I need the space now to do part 2 of this question. Okay. So I'm going to rub that out. But not all of it, because actually I can use. So, again, we'd start the question from the start, part 2 now, okay? The calorimeter is made from copper and it has a mass of 70 grams. So heat lost by steam stays, heat gained by water stays, but what else now is gaining heat? The calometer. So you have to add in plus mass of the calometer. It's made of copper and its temperature goes up. Okay? And its temperature goes up. I just realized now I shouldn't have rubbed out the steam side, but it doesn't matter. Okay, so we'll put all those values back in now. So we'll rewrite in those values. I'll try and squeeze it in a bit better this time. Okay? Actually, you know what? I'm actually going to skip a bit. So because this is the same as above, so this is the same, I'm just going to skip a step here and just basically give it to us as it was. So it worked out to be, I'm gonna leave the left hand side for the time being, and I'm gonna focus on the right hand side because the left hand side was the exact same. Okay, so right hand side. So the right hand side will become for water 334.4 into theta minus 10 plus 27.3 into theta minus 10. That's what you should get because this is the same as above. This is 0.07 and heat capacity of copper was, what did we say that was? Hang on a minute, where's the heat capacity of copper? Copper is 390. There you go, that's it. So 0.07390. They'll give you those values, guys, okay? And that's what we should get, all right? Now, so that's what we should get for the right-hand side. So now I'm going to bring back in the left-hand side. So what did we have on the left-hand side? We ended up with 4, 6, that's it, yeah. 0, 0 plus 836 minus 8.36 theta equals 334.4 theta minus 3344 plus 27.3 theta minus 273. Okay, so bring all my thetas to one side, all my numbers to the other, and I should end up with 370.06 theta. That should be a decimal point, not a weird dash, equals 9053 theta equals 24.5 degrees Celsius. There we go. All right, so 24.5 degrees Celsius. That's it. When I tell you that they're literally all like that, they're literally all like that. You look at the book, Real World Physics, I think it's chapter, what topic is this? Might think they're, so it's topic, it's either 30, chapter 13 or 15, I think it's chapter 13. All the questions are like this, guys. It's basically what's losing, what's gaining, list out your values, put everything in. You write it out on the left-hand side, you detail what's losing, what's gaining, write out your equations, and it'll work every single time, okay? These are the easiest questions to pick up marks in. Now, the next thing I'm going to look at, guys, I'm going to just talk about this, and then I'm going to basically move on to the last bit there, really. The human body cools by respiration. You should kind of know that anyway. So, heat pump. So, the reason I'm going to cover this comes up in modern physics, nuclear physics, whatever you call it, as well. So I'm just going to go through it here. Basically, your fridge, and there's some new things that they have for heating your homes. What are they called again? I can't remember the name of it. But anyway, air to water, that's it. So the air to water system. So basically with your fridge, in your fridge, so your fridge will be this thing here, okay? These things go in, they boil. So what it is they have, all right? They have a low boiling point, okay? As you can see here, okay? Low boiling point. High specific latent heat, low boiling point. So what that means is that when they go in, they boil at, say, 0 degrees Celsius. So when it goes in, it changes now from the liquid into the gas. So to do that, it needs to take in the heat energy from the fridge, and it does. So it turns into the gas. It then comes back out. The compressor forces it back into a liquid. That's why the back of your fridge is hot. It's taking the heat from inside the fridge and spitting it out the back. Why? It's got a high specific latent heat. In other words, it takes in a large amount of heat, but boils at a low temperature. How air to water systems are working is they do the opposite. Air to water systems, if it ever comes up, an air to water system is the reverse. What an air to water system is this is your house and this is your unit outside. And the air comes in and this boils, okay? If your temperature is above -5, this will boil and then come back in here and release the heat into the water in the house to heat your house. And that's how that works, okay? There is solar panels that work on that basis as well, where they can heat your water as long as your temperature is above something like -15 degrees or 5 degrees or something like that. As long as the temperature outside is above -5 degrees or -15 degrees, it'll boil the water in your house, okay? And that's how they do it, okay? You should know conduction, convection, and all that, and radiation. Okay, so solar constant. This question came up as a short question, part of question 5. That's why I'm going to quickly fly through it. What is the solar constant? The solar constant is the average amount of sun's energy falling per second perpendicularly on 1 meter square of the Earth's atmosphere. Okay, the general value is 1.35 kilowatts per meters squared. Okay, just look at the SI unit. They'll generally give this to you in the exam. Kilowatts meters squared. You see? So in other words, it's energy over area, basically. But I didn't really do that because I have the question now, problem 7. This solar panel is the old system, very inefficient. Some still do it, but I think they're better than that. It's a little bit out of date. Okay. So here, problem 7. The solar constant is, they give it to you, 1.35 kilowatts per meter squared. What is the average amount of energy falling on each square meter of the Earth's atmosphere per year? So 1 year. So time. So there's 365 days in a year, 24 hours in each of those days, 60 minutes in each of those hours, 60 seconds in each of those minutes. So okay, 3.1536 by 10 to the 7. So basically the energy, E or Q, whichever, equals solar constant multiplied by time. So E equals 1.35 times 3.1536 10 to the 7, 4.2573 by 10 to the 10 joules. And there you go. That's basically it. That's all they ever really do, guys, is how much, or else they'll give you the average of each square meter of the Earth's atmosphere. They give you a time. They say how much energy falls on the Earth in 2 years, 3 years, 6 months, etc. That's kind of generally it. Okay, that's the end of the topic of heat. Again, as I say, not overly difficult. Those 2 large questions that I did are basically every question in the book, pretty much every exam paper question. Just follow it. What's losing, what's gaining, list out your equations. If there's fusion or vaporization, think vapor for vapor, air, gas. That's for changing liquid to a gas, gas to a liquid. Okay, and therefore fusion is the other. If you have any questions, please leave a comment below, and I'll try and get back to you as quick as possible.